Okay, now we're going to have a closer look at current and potential difference in series and parallel circuits. So what do we know about potential difference? We have to measure it with a voltmeter. We measure it in volts. A voltmeter is connected in parallel, and a voltmeter always has a high resistance. So now remember what I said to you earlier about current being lazy and always taking the easiest route? Okay. So remember, you can't say that in an exam, but I want you to think about it that way because to me it makes it easier. So if you're a little electron that comes out of this battery here and you travel along the circuit here, I won't make my electron noises. So here comes the electron. It comes out of this circuit, out of this battery here, and it gets to this point over here. And at this point, it's got a choice. Does it flow through the resistor or does it flow through the voltmeter? So electrons, when given a choice, will flow through the thing with the smallest resistance. Okay, so they make this voltmeter with a very, very high resistance because you actually want the current to pass through the resistor. It's no good trying to measure the voltage, and then the way you're measuring the voltage is taking all the energy out the circuit. Because remember that why have we got the current flowing through this resistor? We've got the current flowing through this resistor to do work. And if we're trying to measure something and we take away its energy by it going through the voltmeter, it's a big problem. So this voltmeter's got a very, very big resistance. So when the current comes out the battery, it goes wee, 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 gets to here. Okay? And it's like, resistor or voltmeter? It's like, resistor's got a small resistance, I'm going through the resistor. And then there's always a few electrons who are just willing to take the difficult route, and they will pass through the voltmeter, and this allows the voltmeter to make a measurement. And so the voltmeter is making a measurement, and so then most of the energy in the current is used in the resistor, and then it can get back home. But this is why a voltmeter's got a very high resistance, so that a very small current flows through it, so that you can still do work in your resistance while measuring the voltage. Okay, so we measure potential difference with a voltmeter connected in parallel, and the voltmeter always has a very high resistance. So what happens to the potential difference in a series and a parallel circuit? In a series circuit, remember I said to you already, the current is the same everywhere, but the potential difference divides up. So if we look at this circuit here, okay, we've got 1, 2, 3 resistors, R1, R2, R3. We've got some batteries here that are providing a total voltage to the circuit. Okay, so this is my source of energy and potential difference. This is the maximum amount of voltage that can be in the circuit at any time, because that's how much the batteries can provide. So if we have a look, what happens when this voltage leaves the batteries here, when the current leaves the batteries being pushed by the potential difference, as it comes out here, it must travel through these resistors. So if you then put a voltmeter across, voltmeter 1 across resistor 1, voltmeter 2 across resistor 2, voltmeter 3 across resistor 3, what will you find? You will find that the sum of all the voltmeter readings in a series circuit are going to add up to V total. What the batteries are providing is your total voltage or your total potential difference. So the total voltage will be the reading on voltmeter 1 plus the reading on voltmeter 2 plus the reading on voltmeter 3, because a series circuit is a potential divider. Okay, then we look at the parallel circuit. Now this one, potential difference is the same everywhere in a parallel circuit. So we've still got these batteries here, okay, and this battery is still providing a total potential difference, okay, your V total. If we then say what happens, the current comes out here and it can go through resistor 1, resistor 2 or resistor 3. The current can make a choice at this point. That's what parallel circuits are all about. But then you'll see that once it's moved through the resistor, it has to come back and rejoin. All the current rejoins over here, okay, and then it goes back to the battery. The potential difference is the same everywhere. If I've got these same resistors, resistor 1, resistor 2, resistor 3, and I measure the voltage on these resistors, these voltages will be all exactly the same as the voltage coming out the battery, because the battery is actually in parallel with all of these resistors. So potential difference is the same everywhere in a parallel circuit. The voltage out the battery is the voltage across resistor 1, the voltage across resistor 2, the voltage across resistor 3, and we also sometimes call it VP, the parallel voltage. Okay, so that's voltage. Let's talk about current. So current strength, okay, electrical current strength is the rate of flow of charge in a circuit. So if you have a look here, if you've got a large current, you've got a lot of charges flowing. How much charge went past this point? If you've got a small current, you've only got a few charges flowing. Remember, these charges are based on electrons, and that Q is the symbol for charge. So we can think of lots of little Q's flowing past here. So in a large current, lots of charges are flowing. In a small current, only a few charges are flowing. So when we say this definition, electrical current strength is the rate of flow of electric charge in a circuit. This word, the rate of, means that we are dividing by time, okay? So you can't say electric current is the flow of charge. It's not. It is the rate of flow of charge. You have to check how many electrons are passing this point in a second. Is it 1 electron? Is it 2 electrons? Is it 6 million electrons? That is the rate of flow of charge. So it has to be how much charge passes a point in a second, okay? So what happens here in your battery here, or this is like a magnified piece of the current here. So in your battery, okay, this is your source. It gets energy. The charge, the little electrons pick up energy from your source. Chemical energy is converted to electrical energy in your source. And then the moment you close the circuit, this energy travels through the circuit and it gets delivered to the components, the ammeter, the voltmeter, the resistance, whatever, okay? So if you then check this current flowing, you'll get a current reading, okay? So what happens is electrons leave here, they go through the circuit, they come back to the source. Electrons, the charge remains constant, okay? This is the law of conservation of charge. Nothing happens to the charge, but the energy that the charge is carrying gets used up. The resistors take the energy, but let the current carry on flowing. So like, the charge is just like a little energy carrier. So this current is the rate of flow of charge. The current is the rate of flow of charge in symbol form. The current I is equal to the amount of charge flowing past a point in a certain amount of time. So it's current equals Q over delta T. Remember, this triangle is delta, the Greek letter delta, and it means the change in, so the change in time from the final time to the initial time. Delta is always final minus initial. But in your questions in grade 10, they'll just say to you it was 120 seconds or something. Speaking of which, current is measured in amps, charge is measured in coulombs, time is measured in seconds. Nearly always with these calculations, they are going to give you time in minutes. You need to convert it to seconds before you do any calculations. Your units are incredibly important. So this formula, it's actually much easier to remember, equals Q equals I delta T. I think of this as the quit formula because it looks a bit like the word quit. Okay. And so we will use this a lot in calculations. So remember, we know this from electrostatics. It's the same charge because it's the same electron, so it's the same Q. It's measured in coulombs. The difference is in static electricity, the Q is sitting still, and in current electricity, the Q is moving from point to point. Okay? So a coulomb, if you had to define a coulomb is defined as the charge transferred in a conductor in 1 second if the current is 1 amp. So a coulomb, in one sense, is the amount of charge on a certain number of electrons. But if you want to define it in terms of electricity, because they did a lot of things with electricity before they found out about electrons, a coulomb is the charge transferred in a conductor in 1 second if the current is 1 amp. Now, the last thing to remember with current is that in current we've got two kinds of current, because life would just be too boring if there was only one kind. In electricity there's conventional current and there's the flow of electrons, okay? So engineers, people who actually work with electricity and build houses and electrical networks across the country and that, they always use the conventional current. And when we do physics questions all the way to grade 12, we're going to use conventional current, okay? But in chemistry, which we're also going to use this, we're going to learn exactly how this battery works and how you can figure out how much voltage comes out the battery. We'll learn about this in grade 12, and we can even make our own batteries, which we will call galvanic cells, okay? So then, we want to know where the electrons are going in chemistry. So here, the electrons flow out the negative terminal. Can you see here? The small terminal is the negative terminal. I always think of the positive terminal. To make a plus, you must draw two lines. So that's why, to me, the plus is longer, because a plus takes more energy to draw than a minus. So the negative terminal here is the small one, and electrons flow out the negative terminal and back in the positive terminal. But if we're doing physics questions, we worry about the conventional current, which comes out the positive terminal and returns to the negative terminal. So this is it summarized. Conventional current is from plus to minus. Electron flow is from minus to plus. So here's electrons flowing, but current is going plus to minus, conventional current. It's just the way it is. Live with it. So the flow of current is given the symbol I. The unit of current is the amp. An amp is technically a coulomb per second. We measure it with an ammeter. We place ammeters in series. We want to find out how many electrons are passing this point in a second. And the only way we can count them is to get in their way. So how many electrons went from here to here? You have to stand in their way. But now what is the job of this charge moving through here? Its job is to do work. If we put a big resistance in here, all of the electrons are going to drop off the energy in the ammeter, and that's not okay, because we actually need the current to still go and do work, okay? So the ammeter has a very low resistance because the electrons have got no choice, because to measure them, they have to flow through the ammeter. So here the ammeter's got a low resistance, so the current carries on mostly unaffected. If we look at current in a series and a parallel circuit, remember right at the beginning, in a series circuit, the current is the same everywhere. So here in this circuit here, resistor 1, resistor 2, resistor 3, here's an ammeter in series, an ammeter in series, an ammeter in series, an ammeter in series. In all of these, okay, this total current is equal to the current at any point in the series circuit. So the total current is the same as the current at ammeter 1, the same as the current at ammeter 2, the same as the current at ammeter 3. In a parallel circuit, it gets a bit more interesting, because a parallel circuit is a current divider, okay? So now, if you have a look here, here comes your current out of the battery here, passing through this ammeter here, and then when it gets here, the current can choose to split up. Now remember I said to you, the current will always take the easiest path. So if these resistors have different values, the biggest resistor will have the smallest current, and the smallest resistor will have the biggest current, because the relationship is inversely proportional. But what I do know is that if I've got this current in the external circuit, and I add up the current passing through resistor 1 plus the current passing through resistor 2 plus the current passing through resistor 3, they will give you the total current, okay? So the total current will be the sum of the reading on all the ammeters, because this is a parallel circuit. And you have to find a way to remember these differences in your brain. There's no getting around it. You have to know that in a series circuit, the current is the same everywhere, and in a parallel circuit, the current is divided. When I remember these things in my brain, I always fix the 1 in my brain. In a series circuit, the current is the same everywhere. And from there, I don't try and remember two things at once. I remember this one thing, and then I use logic to figure out the other one. Series and parallel are different. So series, the current is the same. And then I think, okay, parallel is different. So what's happening? The current can't be the same. It must be split up. Okay, so let's look at this before this gets too long. So what happens now is if you add more resistors in series, the total current is the same everywhere. So if I've got one resistor, I've got one current. If I've got two resistors, I've got a different current. Okay, so remember resistors, remember that picture right at the beginning of that little ohm in his cowboy hat squashing the current while the current is trying to squeeze through. So the more little ohms you have squashing the current, okay, the more resistors you have in series, the harder it is for the current to pass. So the more resistors are in series, the more the resistance increases, and then the current flowing through the battery gets smaller and smaller and smaller. So the bigger the resistance, the smaller the current. This is what happens when you add more resistors in series. The current just starts dropping off. But if you add resistors in parallel, okay, the electrons can now make a choice. So if you add resistors in parallel, the current increases wildly, okay, and current's actually what causes heating. So if you put too many parallel resistors in, things tend to get hot and explode. So if you add more resistors in parallel, the electrons have more routes to flow through, which means there's actually more current flowing with parallel resistors. And the more parallel resistors you have, the more the resistance decreases. This is a very hard thing to get your head around, but more resistors here is smaller total resistance when the resistors are in parallel. So if you take a resistor out, look over here, the resistance actually increases in parallel. It's very weird. We'll do some look at some calculations with it just now. So the more resistors you put in parallel, the total resistance decreases and the total current through the battery increases. Just strange, and that's the way it is. And we'll come back just now and look at resistance.